We trust maps. We rely on them to show us the world as it is. But what if I told you that every single map you've ever looked at is telling you a lie? A necessary lie, maybe, but a lie nonetheless. And what's really wild is that this exact same kind of deception is hiding in plain sight in the charts and visualizations that scientists use every single day to make huge discoveries. So let's get into it.
It all starts with a deceptively simple question, the kind a kid might ask. How do you take something spherical, like a globe or even just an orange peel, and flatten it out on a table without squishing, stretching, or tearing it?
Well, the short answer is you can't. It's literally impossible. Every flat map of our round Earth has to make a compromise. If you want to keep the shapes of the continents looking right, you have to mess up their sizes. That's why Greenland looks as big as Africa on some maps. And if you want to get the sizes right, then you have to distort the shapes. There's just no way around it. It's a fundamental trade-off.
Okay, so here's where it gets interesting. Researchers are facing the exact same problem. They're basically digital map makers. But instead of flattening a globe, they're trying to take this incredibly complex, high-dimensional data. We're talking about things with thousands of variables, like genetic codes or financial markets, and flatten that into a simple 2D chart that our brains can actually make sense of.
And for years, one of the go-to tools for this job has been a really clever algorithm called TSNE. Think of TSNE as the superstar software for making these data maps. It's used absolutely everywhere, from biology labs to machine learning startups.
But, and you knew there was a but, here's the catch. Just like those old world maps we talked about, TSNE's maps have a hidden flaw. And it's a flaw that can be more than just a little wrong. It can be dangerously misleading. So take a look at this. This is a classic t-SNE plot. And at first glance, it looks pretty great, right? You've got these beautiful, tidy little clusters of data. And t-SNE is fantastic at one thing, showing you which data points are immediate neighbors. If two dots are right next to each other on this map, you can bet they were neighbors in the original complex data. But, and this is the big one, the empty space between these colorful clusters, it often means absolutely nothing. Two clusters might look miles apart on the map, but in reality, in the actual data, they could be surprisingly similar. This is the absolute core of the problem. TSNE is a master of preserving what we call local structure. The relationship between a point and its closest friends. But it is terrible at preserving the global structure, the big picture layout of how all the groups relate to each other. It's like it's so focused on mapping out individual neighborhoods correctly that it completely forgets to show you which city those neighborhoods are in. It shows you the trees, but it completely hides the forest.
And that is where some fascinating new research comes into play. It offers two really clever fixes, two brand new tools for our digital map makers that promise to build much more honest and trustworthy maps of our data.
Okay, so solution number one, we can think of it as the ranking fix. Its technical name is KL-Max, and its genius is in how it rethinks what's actually important in those local neighborhoods.
See, the old TSNE just tries to keep all your friends nearby. But KL-Max says, nope, that's not good enough. It says what really matters is making sure your best friend is always the closest one to you on the map. Your second best friend is second closest, and so on. It's all about preserving the ranking of those relationships. And that simple change creates a much more faithful picture of what's going on locally.
The second fix takes on that much bigger problem of the global structure. We'll call this one the geometry fix. In the paper, it's called LKL way. And this idea is just so cool. It borrows from a field of math called optimal transport. The best analogy is to imagine your data as a big pile of sand. This method calculates the most efficient way, the path of least resistance, to move that pile of sand and reshape it into your 2D map. By focusing on the most efficient journey for the whole pile, it manages to preserve the overall geometric shape of the data. It finally gives our map a sense of the big picture.
All right, so that all sounds great in theory. But does it actually work? Let's take a look at the payoff. The before and after pictures here are pretty stunning.
First up, here's a data set of different objects being rotated, all mapped out with standard t-SNE. Honestly, it's kind of a tangled mess, isn't it? The loops, which should show the object turning smoothly, are all crowded and twisted up. It's really hard to see what's going on globally.
Now let's apply that first fix, the ranking fix, or KL-Max. Okay, see that? The clusters immediately sharpen up. They're more distinct, less of a jumble. The local neighborhoods are way clearer. It's a definite improvement.
But now for the big reveal. Here's the exact same data, but this time mapped with our geometry fix, LKLW. Wow,
I mean, it is a night and day difference. Not only are the individual clusters sharp and clear, but the global structure, the actual spacing and arrangement of those loops is finally obvious and meaningful. This is a map that tells a much more truthful story.
And hey, it's not just our eyes telling us it's better, the numbers back it up big time. Using a score for clustering quality where higher is better, you can see this clear progression. The standard method gets a 0.851. The ranking fix bumps that up to 0.865. And the geometry fix, it comes in with the top score of 0.888. The proof is in the data.
So this brings us to the big question. Why does any of this actually matter? I mean, who cares if the dots are arranged a bit better? Well, it matters because these are not just pretty pictures.
Think about it. In biology, a clearer map could be the difference that helps a scientist finally spot the subtle pathway of how cancer develops in cell data. For things like facial recognition, or even just searching your photo library, a map that truly understands the global relationships between images is going to give you far more accurate results. Plain and simple. Better maps lead to better discoveries.
Now, to be fair, it's not a magic wand just yet. These new methods are more advanced, which means they do take more computer power and more time to run. And they also come with a few new knobs and dials that need to be tuned carefully to get these amazing results. As with everything, there's always a trade-off.
But the path forward from here is incredibly exciting. The next logical steps are to try and combine the power of both of these fixes into one super method, figure out how to make them run faster, and maybe even get them smart enough to tune their own settings automatically. So, if you're going to take away 3 things from all this, let it be these. First, most of the data maps you'll see are telling a half-truth. They're great with the little details, but they hide the big picture. Second, a couple of clever new fixes, one focusing on ranking, one on geometry, can now create maps that are way more trustworthy. And finally, and most importantly, better maps mean clearer insights, and that helps speed up the entire process of scientific discovery.
It really makes you wonder, doesn't it? With the insane oceans of data we have today, in medicine, in climate science, in astronomy, what incredible, world-changing discoveries are already out there, just sitting in plain sight, waiting for someone to finally come along and draw the right map.